guess I have to warn you that what we're doing today here, the natural log function integration is section 2, right? You better be prepared, because what did we just spend 2 days doing? Differentiation, right? And so there's this whole, now we're going to go backwards with the same function. And you did this in Calc 1, but you have to be able to go back and forth very quickly. I guess that's the deal. And in some ways, putting together this particular PowerPoint is pretty boring. I mean, here's a quick flash through of what's going to happen. So here, let's do this. Okay, so it's going to be like integrate this, integrate that, integrate those, integrate that, and then let's do some trig functions. Okay? I mean, that's the lesson plan. So I have to tap into, do you guys remember things about integration, right? So we did some review last time, our first class, but I don't know, maybe this will help. I think I stopped recording. Okay, so let's get to it. We want to integrate a function like this. Can I do it? Well, I guess the point is that from the fundamental theorem of calculus, part 2, which is really the answer to your quiz question, right? The antiderivative and the guy inside the integral, they're related, right? So here, let me get that. Oh wow, 2 choices. Let's go with that. So I don't like that already. Okay. So I want to integrate this guy. Well, I'll use a formula. I have a derivative formula. And the derivative of what? What's the formula we know? Yeah, we'll try again. D over dx, the derivative of the natural log. That's what we studied last time, right? So what's your formula? This could have been a quiz question as well, I guess. The derivative of the natural log of, say, x is what? 1 over x, right? So if you have a formula for differentiation, automatically, what do you have? A formula for integration or anti-differentiation, right? Depending how you want to say it. So the corresponding formula, I guess, is that if I instead come down here and I write integral 1 over x dx, what is that? Natural log of x plus c. Now, there is a little caveat here. And that is, remember that when I wrote down what this function even represents, what was the domain of the natural log function? Yeah, from 0 to, well, actually, it has to be greater than 0. Yes, greater than 0. Right? The open interval from 0 to infinity. And so if I'm going to preserve that, I need to make sure that x is positive. Or in other words, what I can do is I can write this. The natural log of the absolute value of x plus c. And I guess I didn't do this last time, but it's also true that if you put absolute value bars around the x, you also get that. And that's actually proven in section 1. Okay? Because if x is positive, this is definitely true. We already know that. And if x is negative, it turns out you get a negative over a negative because you get u prime over u, and it works out nice. So here's your formula that basically is going to kind of carry you through this section. Okay. So we're going to integrate from 1 to the square root of e of this guy. So, using the formula, that's the natural log of the absolute value of x. Oh, but I don't need a plus c because I have a definite integral, right? So I'm just going to write down that I'm going to evaluate this guy from 1 to the square root of e. So what does that equal? Well, both of these guys are positive, so the absolute value doesn't matter here. It will some places. Okay. So I just want to make sure I pointed it out. So I get the natural log of, let me write it as e to the 1/2 minus the natural log of 1. What's that equal? This is 1/2, right? How do you know? Right. How do we know that? See, I guess I kind of cheated here. Because in your book yet, we still haven't said what this is, e. So I'm tapping into knowledge, and I'm about to use circular logic, okay? Actually, we'll define e today to be just the right number in a sense. We'll see exactly what I mean by that today, okay? It's just the right number. But yes, if you want to say that, so what's the relationship, I guess, between the natural log function and the exponential function? What's the relationship? What's that? Yeah, so we have this relationship. That's actually one way you could define e. So we'll define e to be the number that if you take the natural log of it, you get 1. So you could almost, I didn't do this yet, but I could say definition, we're going to define the natural log of e to be 1. That's coming later today. Okay? Now, if I have that, then I'm set, because now what can I do with this 1/2? Put it out front. And so I get 1/2 times 1, because the natural log of e then is 1. Minus, and what's the natural log of 1? We did that last time. That could have been a quiz question. That's 0. Right? Yeah, so that's nice. So using log laws, John pointed out that we could do, this is the natural log of e to the 1/2 over 1. Right? We talked about those log laws last time. And so then you don't need to worry about the 0. But either way, we're going to get 1/2. Of course, the nice thing about a definite integral, I can check that, right? If I can pull out a graphing calculator. Let's do that. Where? Here. Where is it? There it is. So you guys all know how to do this, right? Just in case. Okay, so let's get this out of the way. Excuse me. And over here I can say, okay, I want to do second. Let's get rid of that. So let's do y equals screen. And what do I want to plot? It was 1 over x we were integrating, right? So I could say 1 divided by x, and I can graph it. Just I'll do the standard zoom, choice 6 under zoom. So there it is. Okay, I could zoom in maybe if I want a better view. I'll zoom in. There it is. And now, let's see, I want to integrate. So I can do second calculate. Try again. Second trace is calculate. And down here, choice 7 lets me integrate. Lower limit 1, upper limit, well, I can say second function natural log. See, they're related. E to the x and natural log x. They even put them there on the calculator. I want to say what the relationship is. To the 1/2 power, so I'll put 0.5. There it is. When you integrate from there to there, that area is 0.5. Okay? All right, put that away for a little bit. We're trying to integrate this guy. So here's an indefinite integral if you want. So what's the technique? How would you start? You could write it that way if you want. That's equivalent to this. Yeah. Substitute, right. I mean, that's the whole theme of today, is that we have this powerful tool for integration. Substitution. If I let u equal the denominator, what do I do next when I do an integration by substitution? I compute du. So what does du equal? Okay, let me do an intermediate step. What I'm really doing is du dx, right? U here is a function of x. It's 2x minus 1. So then what is the derivative of u with respect to x? 2. So another way to write this, which is a differential equation, is you can write du equals 2 what? Dx. And if these steps here seem shaky, you're going to want to, sometime over the next 2 weeks, go back to those optional problems I mentioned, section 4.5, integration by substitution. Okay, that's what you want to do. You want to take a look at those on your, sometime before the first exam. And what some teachers teach next is that you want to actually solve for dx. What does dx equal? Well, if du is 2 times dx, dx is 1/2 of du. Is that okay? And the idea is now I can rewrite this integral. Now instead of writing 1 over 2x minus 1, I have 1 over what? U. And instead of dx, what can I write? 1/2 of du. And so you can write du here and pull the 1/2 out front. Because the 1/2 is a constant, it's not going to affect it. Okay. This is one way to get from that integral to that one. And once you get this far, you're in good shape. Because now, what's the answer? It's 1/2. What happens when I integrate this guy? That's the natural log of, and again, I'm going to say the absolute value of u plus c. And the only thing you have to remember now is, okay, we didn't really want u's. We wanted to know in terms of x, what's the answer? And so, maybe as a final answer, I will say, what? Natural log of, what do I say instead of u? 2x minus 1. And here's something that the back of the book might do. They might bring that 1/2 back up front here, and then turn the 1/2 into what? Yeah, the 1/2 power is also a square root. So if you want to, we could write it this way. Okay? Well, let me ask you this. When I take the square root of something, it has to be positive anyways. If it's negative, then that doesn't make any sense. Yeah. So that was a good question. I guess it's kind of implied that 2x minus 1 is positive here. So can you take the natural log of an imaginary number? Yes, you define the natural log differently. So I want to stay away from that. Okay, cool. 2 more problems here. Like I said, the lesson plan was kind of easy. We have to learn how to integrate. We're going to have to practice. Maybe I'll pause while we just think for a little bit. Like, what do you do with problems that look like this? That was so much fun. Let's do 2 more. So we want to integrate here. I'm a big fan of let's think before we act. Imagine this is a test or a quiz. Which problem should I do first? Talk to your neighbor about it. Go ahead. How many of you agree we want to work on the one on the right first? How many want to work on the one on the left first? And how many have no idea? Okay. And how many haven't voted yet? Wow. All right. Well, let's see. See, the nice thing about this one on the right is that I can rewrite it as the integral of x plus 3 to the what? Negative 1/2, right? dx. And that's kind of nice because I think if we substitute now, we'll be liking what we see. Let's see. Let's let u equal what? X plus 3. And if I do that, du equals dx. So again, I don't have to be so nice. I could put 2x plus 3 under the square root, and then du is 2 dx, right? And then you have to be a little more careful when you do your substitution. But the point I'm trying to emphasize here, I guess, is how you handle that square root down there. And I also want to emphasize that, yeah, I think this one's nicer than that one. I think. Because when you work this out, let's see what we get. We get the integral of u to the negative 1/2 du. Okay? And I think that's very doable. That's basically like a polynomial, right? Where what happens? Well, the first thing I point out is that the antiderivative, what exponent am I going to have here? Positive 1/2. It has to be one more than this so that when I take the derivative, I'll get what was in here. And if I took the derivative, I'd be taking that 1/2 and bringing it out front. So I need a 2 here, right? And that you did in Calc 1 quite a bit. So bring the 1/2 out front. It would have to cancel with that 2 to get that. Good. So it's 2u to the 1/2 plus c. And so I guess the final answer for this one is 2 square root of x plus 3 plus c. That's not too bad. It's like a two-liner. Question? Okay. Now, the other one. This one's not so friendly. You could write that x to the 1/2 and you won't like what you get. It's just not that fun. Okay, so I'm going to share a trick with you here. Because this one takes time. Let's let u be the square root of x. That's a good hint. Now, if I give you that hint, what's your next step? After I write down u, when I do u substitution, what's the next thing you've seen me do every time? Compute what? du. I want to compute du. So could you guys do that for me? Write down what du equals. Right, so let's see. So du, if I think of this as x to the 1/2, du is 1/2 x to the negative 1/2, which is, if you want, 1 over 2 times the square root of x. And don't forget that this is, I need to put a dx here also. So let me see. du equals 1/2 x to the negative 1/2 dx. What are you saying? Oh, right. So if you wanted to solve, if you wanted to put the number on the other side, you can. You could say 2 du equals I guess it's 1 over the square root of x dx, right? Where do I have it? Oh, here? Almost. I have that plus 3, which is annoying. See, when you have a plus sign in the numerator of a rational expression of a fraction, that's nice. But if you have a plus sign in the denominator, not so nice anymore, right? Like if I have 1 over 2 plus 3, notice that does not equal 1 over 2 plus 1 over 3, right? It's just no fun. So, yeah, so this is trickier. You know what I'm noticing is that 2 du actually equals 1 over u dx. Because what did we say u was? The square root of x. Why does that help? Because what does dx equal in relationship to the u's? Do you see it? Two u du. 2 u du. I can bring that u over here just like I brought the 2. I guess I could have done it in one step. Move the 2 square root of x over and solve for dx. I did it slowly. May have been worse. I don't know. Okay. Well, it's time to rewrite the integral at this point because I think I have everything I need. Let's see. What does 1 over the square root of x plus 3 now become? 1 over what? U plus 3. And then, where it used to say dx, through my long computations, we figured out that that's actually 2u du. So let's see if this is going to work. 2 times the integral of u over u plus 3 du. Now what? Are we any better off? Well, at least the square roots are gone. It's too bad that the plus sign's still in the denominator. Yeah, idea? No. It's u. That's right. That's exactly what you want to do next. So remember that this is u divided by u plus 3. So Clayton wanted more practice. Here it is. You can practice now your long division of polynomials, and while you do that, I'm going to pause this because we don't need to hear that. Okay. U divided by u plus 3. I put a 1 there, right? 1 times u plus 3 is u plus 3. Now I'm going to subtract. I need a new color for that. Go green. So when I subtract the u plus 3, the u's are gone, but I have a negative 3 for a remainder, right? So right now, let's see where we are. This equals 2 times, and what I'm integrating is 1 minus 3 over u plus 3 du. So I'm going to get, and you know what? Honestly, I might actually take that 2 and distribute it. So it's 2 minus 6 over u plus 3. So I'm going to get 2u for the first part minus 6 times the integral 1 over u plus 3 du. Is that okay? I still have to do the other integral. Question? It 2 times 1, and I'm going to integrate it. So I'm just integrating 2. And I still have to integrate the other one. Now, when I integrate the other one, how am I going to do it? Okay, I guess V substitution. Sure, you need something else, right? Oh, purple. Nice. So, let's see. 2u minus. Let me just suppose you did the V substitution that you're talking about. Notice that V equals u plus 3. Then dv is the same as du. And it all works out nice. Okay? So you're going to get 6 times the natural log of what? The absolute value of the u plus 3 plus c. And now I'm almost done. What's the only thing I have left to do? Put the square root of x back in. Okay, so final answer looks like 2 square root of x minus 6 times the natural log. Oh, cool. I don't need the absolute values because square roots are always positive. So I can put square root of x plus 3 here plus c. There's a final answer. You know, I'm questioning myself on an earlier problem. I'm going to jump back to it in a second. You guys asked, what happened to the absolute value? And I said, oh, we don't need it. We might need it the more I'm thinking about it. I'll look back at it in a second. Here. What was that problem? Here. Right here. Yeah, I need this to be positive, guys. I need to make sure 2x minus 1 is positive, right? So just to make sure of that, I think I want my absolute values there. Yeah.
The absolute values, you just carry both go outside.
Well, but no, because the root came up here, right? So I do need that absolute value around that 2x minus 1. Yeah. But in this situation, this is different because here u is positive, always. When you take the square root of something, you're not going to get a negative number.
I didn't check out 3, but I think you got it. So you get 1/3 e to the 3x plus c. And then for this one, I guess it would be 4 times exp of x over 4 plus c. Again, I can take the derivative. When I take the derivative of the exponential function, I get itself back. But then by the chain rule, I'd have to multiply by a 4th. And so I guess number 5 I would write as e to the mx divided by m plus c. Okay? Moving on. Number 6. Ooh, okay. How do I do this one? What'd you guys let u equal? Anyone? Okay, that's a nice trick. If we let u equal e to the 2x plus 3, then when I compute du, well, I'll get back e to the 2x, but I'll have to put a 2 in front. 2e to the 2x dx. Yeah, so we can rewrite this as 1/2, and now we have the integral of du over u. Right? So the 1/2 puts the 2 where I need it. So this is 1/2 the natural log of the absolute value of u plus c. So this is 1/2 the natural log of, well, of what? Do I need absolute values? I say no, because what? I have a better reason. What's the range of the exponential function? It's always positive, right? And then I'm just adding 3 to some positive number, so it's positive. So I guess I don't need the absolute value. So you could have this. You could also write this. Some people, instead of the 1/2 here, where are you going to put it? Up here, and then people might do this. Does that make sense to people? And then some people get really crazy, and instead of writing c, they'll write the natural log of some constant. And you might say, why would they do that? Maybe because they want to use a log law that lets you put these natural logs together, and they'll write something like the natural log of c square root of e to the 2x plus 3. There's a lot of weird ways to do things. Okay, any of these are good. 7, 8, and 9, which one can you not do? We did 7. It's 8. 9 works, doesn't it? How do you do 9? Let u equal x squared, du equals what? 2x dx, and so 2 in there, so I have 1/2 integral e to the u du. I was lucky that I had an x. Yeah, number 8 cannot do. Cannot do in Calc 2. Cannot do in Calc 3. Cannot do at all. It's not in terms of elementary function. Unless someone came up with a u substitution I'm not thinking of. No, I know you can't. You have a question? Mike? What do I mean by this definition? A to the x equals e to the x times ln a. Here, when I write that down, a to the x equals e to the x times ln a. What I'm trying to do here is imagine that a is any number you want. My favorite example is 2. 2 to the x power. Because we know lots of values. When you're a little kid, you probably played this game. You just start doubling, right? 2, 4, 8. Go ahead. Tell me the rest. My favorite is 2 to the 10th. That one's easy to remember. 2 to the 10th is 1,024. Okay? It's easy to remember, but all these numbers double very quickly, right? So, but what about, how are we going to define this function in calculus class? Because in calculus class, remember, we didn't define e to the x first. What we did first was we defined the natural log, and then we got e as its base. That was the number that gave me an area of 1 under a certain curve. Okay, well what I claim is that we can define it in terms of e. Once you have one exponential function, you can get the rest of them. Okay? Now how do I see that? Well, if I have e to the x ln a, and by the way, ln a here, in my example, would be the natural log of 2. I'm claiming this is going to be e to the x times the natural log of 2. Okay? So, what I'm saying is, let's see, how am I going to say this? Oh, here we go. You see this x? We wrote it in front of that natural log right there, right? So according to the log law, where can I move it? Right up there, right? And so I can write, this is the same as e to the natural log of a to the x power. Are you with me? Well, e undoes the natural log because they're inverse functions. F of g of x is just x, right? And so that shows that this should be a to the x power. You guys with me? So why do I say this is a definition then? Well, this works for any rational base, but we're gonna allow a to be any number at all. Things like pi. I don't even know what that means. Pi as an exponent? Well, 3.14 is a rational number, but pi is irrational. See, in general, if I have something like this, x to the p over q power, what do these things mean? When you have a fraction exponent, what do the p and q tell you to do? Okay. The q is the root, right? But if I say x to the pi power, what the heck does that mean? Yeah, but that's, how do you, I mean, I know how to multiply something by itself 4 times, but I don't know how to multiply something by itself pi times, right? And I can't even write it as p over q. I can write this, x to the 22/7 power. Is 22/7 the same as pi? Are you sure? Let's see. Let me clear things out. If I type in 22/7, is that the same as pi? Almost is right. Okay? So they're close, but they're not the same. So people that say use 22/7 instead of pi, well, it's close. So what I would say is this function, x to the pi power, is close to this function, x to the 22/7 power. And what you do basically is you get functions that are closer and closer to what you want, and the limit is what you call the exponent of pi. Okay. Too much. Okay, but what I'm going to do now is I'm going to use my definition to do a few problems. Guess what we're going to do? We're going to differentiate, and then we're going to integrate. You got to be able to do both. Okay? So it's just basically, once I give you the definition of the function, you ought to be able to use it as needed. Okay, so let's do it. 3 to the x squared power. So let's suppose I want to compute the derivative. Well, how would you do that? Let me say what you won't do before I say what you will do. This does not equal something like 3 to the x squared minus 1 or something like that. You can't subtract 1 from every exponent in the world. That only works for polynomials. Okay? So I'm in trouble here. Unless I use the definition to rewrite it. I don't know how to find the derivative of 3 to the x squared, but what I can do is I can rewrite this as e to the what? To the x squared times what? Good. It's like I take the natural log, and then I e to the, I take the exponential. And that allows me to bring the x squared down in a sense. Does that make sense? So if I had written it this way, f of x equals this crazy thing, there's a chance you guys are going to get it right now. Let's try it. F prime of x equals, well, it's an e to the. So I get back e to the x squared ln 3 times, bong, the derivative of what? Of x squared times the natural log of 3. Does that make sense? You take the derivative of the inner function. Now, Ryan, you said product rule, and that's a good hunch, but I will say one thing. We don't have to use it here because what do I know about the natural log of 3? That's just some number. It's a constant, right? So I can kind of ignore it because, its derivative is 0. So I guess what I'll get for the derivative is e to the x squared ln 3 times, and what's the derivative of this crazy thing? Well, let's write down the natural log of 3 again, because that's just a number. And so what do I get? 2x times this stuff. Yeah. So if I had to write this out, I'd probably write f prime of x in the following way. Let me write this piece first. So we have 2 times the natural log of 3 times x times, now I want to do something. I don't want to write this anymore, because didn't I start with a form that was a little bit cleaner than that? What am I going to write? Times 3 to the x squared power. There's your derivative. Okay. You guys see how that works? Here, try another one. See if you can get one. Try this one. Let's integrate this thing. 10 to the square root of x over the square root of x dx. So again, I gave you a rule to use. Oops, I'll save that one for later. I gave you a rule. Let's see if we can use it. So the new problem is 10 to the square root of x over the square root of x dx. Yuck. Oh, what's the rule? The rule is a to the x power can be written as e to the x ln a. So, let's rewrite this using that rule. So I still have my square root of x down here. What am I going to put in the numerator instead of 10 to the square root of x? There you go. E to the square root of x ln 10 dx. Wow. Well, I have some work to do. Any hunch on what I might want to let u equal for my substitution? Yeah, let's make it the whole thing. Square root of x times ln 10. In other words, I could rewrite that. U is x to the 1/2 times the natural log of 10. Right? Okay. I need to compute du. What does du equal? Times the natural log of 10 still. No, it's a constant. It's kind of like if I have 17x squared for g of x, then what's g prime of x? Well, it's 17 times 2x. We just ignore the 17. Here I kind of ignore the natural log of 10 for a while. Okay? And by the way, I guess my question is, do we have du? Not quite, right? Oh, I forgot the dx here when I put the du. I do have dx to the negative 1/2, right? I mean, another way to write du, I guess what let me write down what Ryan was just saying. He said what we have is 1 over the square root of x, and we have our dx. But what I don't have is this piece and that piece. So I guess what you have is 2 du over the natural log of 10. I have to multiply by 2 and divide by the natural log of 10. And now I have what 1 over square root of x dx is. So I'll be able to substitute in for this stuff right here with the blue, and then I'll have e to the u. So I'll go ahead and work this out. I get e to the u times, well, 2 over the natural log of 10 du. And the 2 over natural log of 10, that's a constant we can bring out front. So I get 2 over the natural log of 10. Oh, what's the antiderivative of e to the u? E to the u plus c. So the final answer, well, not quite the final answer. I'll write this as 2 over the natural log of 10 e to the square root of x natural log of 10 plus c. But I'm going to do one more thing. Yeah, change this back to what? Yeah, because we bring that square root of x up, right? So the final answer would be 2 over the natural log of 10 times 10 to the square root of x